In this video, we are going to take a look at continuity. We'll look at some examples and the definition of continuity. Keep in mind, this is for a brief calculus class, so we're not going to get too heavy into the theory, but we will look at the formal definition. But before we do that, we just want to look at some pictures here. We have 4 graphs. I'll scroll down so we can see them all in a minute. But we just want to, without even discussing what the definition of continuous is, I think you guys probably have a pretty good idea what it means. For example, graph A that I have right here, if I were to ask you, does that represent a continuous function, yes or no? Just go with your gut. What do you think? Well, the answer is yes. You can see this is a nice smooth curve with no holes, no gaps, no jumps. It keeps going and doesn't stop. So this one is yes, this is a continuous function. But if we move over here to graph B, you can see that this graph right away, we see it comes in 2 different pieces. We have this part down here, and we have this part right there with a hole in between the two. So even though we haven't talked about the formal definition of continuity, you probably can imagine that that one is no, that is not continuous. Right here, graph C, it looks at first glance like a nice parabola, but then we notice right here, we got that little hole, and it's a point down here instead. So we can see that that's not a continuous function because it's got to stop right there at x equals -1. But then this next parabola, graph D, it is nice and smooth. It doesn't have any holes like the last one had, so that one is yes, that is continuous. So when you're looking at a graph informally, we can say a graph is continuous if you can trace the graph without lifting your pencil, which you can see we were able to do here in letter D. We can just trace that parabola. But right here in letter C, when we get to that point, we would have to pick up and jump over it. So that's why we got continuous for D and not continuous for C. We do, however, have a more formal definition that we're going to use in calculus, and that's what we'll look at here next. The setup says here, let C be a real number in the interval a to b, and let f be a continuous function whose domain contains the interval a to b. That's just kind of the setup, not important details. The function f is continuous at C when these conditions are true. Okay, so C is going to be some number, like maybe 1. Okay, our function is continuous at that value, at that x value, if f of C is defined. So like I said, if we were using 1 for C, that means if we plugged the number 1 into our function, we would get an answer. It wouldn't be undefined there. That's the first condition. The second condition says that the limit as x approaches whatever number we're looking at of our function has to exist. Okay, we can't have a limit that doesn't exist. That's condition number 2. And then condition number 3 actually kind of looks back at the first 2 conditions. It says whatever answer we got from condition 1 and whatever we got from condition 2, those 2 answers have to be the same. So not only does it have to exist at the value C and the limit has to exist at the value C, but we need those 2 values to be equal. That's the third condition. If all 3 conditions are not met, then what we have is a discontinuity. We have a point where our function is not continuous, and we can have 2 different types of discontinuities. We could have a removable discontinuity, which looks like a hole in your function. So that would have been like letter C here in our first few examples that we looked at. That is a removable discontinuity. Or it would be called a non-removable discontinuity, and that looks like a jump. So for example, that would be what we saw up here in letter B, that first graph that we looked at. We're not going to talk too much about the type of discontinuity, but we will look at that briefly in some graphs. And one other fun fact about continuity, I know you guys do think this is fun, don't you? It turns out that a polynomial function is continuous at every real number. So if you are given a function and asked if it's continuous, yes or no, if that function is a polynomial, like a quadratic function, a cubic function, you just know the answer is yes, it is continuous at every real number. Similarly, if we have a rational function, that means rational, remember, means fraction. Okay, so a rational function would be something like 1 over x plus 2. That's one example of a rational function. A rational function is continuous at every number in its domain. Okay, so if you have a rational function and you're asked about continuity, you need to go back and look at its domain. And we'll get to some examples using those two ideas in a minute. So first of all, we're going to discuss continuity by looking at graphs. In this example, it says for the following graphs, we want to answer these questions. First, is the function continuous? If not, which condition from our definition was not met? So if you say it's not continuous, I want you to be able to tell me why. And then, if it is not continuous, is that discontinuity a removable or non-removable discontinuity? And then we can also answer, finally, if it's not continuous on the whole interval, on all real numbers, on what intervals is it actually continuous? Okay, so let's answer those questions for this first one, graph number 1. You can see we have a nice smooth parabola here, but with a hole right at our vertex, okay? So the first function, is it continuous? Yes or no? Well, it's got a hole right there in plain sight, so no, it's not continuous. And then why not? So we had those 3 conditions at the beginning. And of course, by looking at the picture, we can see that it's not continuous by the hole, but we want to be able to address which condition is not met here. So the discontinuity, we can see it's not continuous at, right here at this point. So that's at x equals 1. So it's not continuous at, I should have wrote that in there, at x equals 1. Okay, so that's going to be the letter C that we're looking at. Okay, so that's the value. So the first thing we need to see, does f of c exist? So if we were to try to figure out what f of 1 is equal to, well, you can see here at f of 1, we have an open circle, and there's no other point at x equals 1. So it does not exist. So that means that condition 1 is not met. That's the reason this function is not continuous. And is this a removable or non-removable discontinuity at x equals 1? It is removable because it is just a single point. It's not a jump. And then on what intervals is the function continuous? Okay, well, you can take a look over here on this side. This whole side is continuous, right? We could trace that whole section without lifting our pencil. So it is continuous from negative infinity until we get to 1. That's where our discontinuity happens. And it's also continuous over on this side. Okay, so it's also continuous from 1 to infinity. We just have that discontinuity at x equals 1. Okay, let's look at another one. This one looks very similar. We have another parabola. It's upside down this time. And we have another open circle. But here we have a solid dot that takes the place of that open circle there where we didn't have the solid dot in the last one. So first, is this continuous? Well, the answer is no. It's got a discontinuity, so it's not continuous at x equals, right here, x equals negative 4. Okay, so it's not continuous at x equals negative 4. Why is it not continuous? Well, we go through our conditions. The first condition is that we have to be able to plug that in. F of negative 4 has to exist. And f of negative 4, although we have an open circle here, we have a closed circle here, so it does exist. F of negative 4 is equal to negative 6. That means the point negative 4, negative 6 is part of our graph. So the first condition is met. F of negative 4 exists. The second condition says that the limit as x approaches negative 4 of f of x has to exist, okay? So we want to look here what happens as we get closer and closer to x equals negative 4. Well, you can see as we come in here from the right, as x gets close to negative 4, y gets close to 3. Same things happens if we come in here from the left. As we get closer and closer to negative 4, we get closer and closer to y equals negative 3. So our limit is equal to negative 3. So condition 2 is met. Okay, but condition 3, remember, looks at our first 2 results. It says that f of negative 4 has to equal the limit as x approaches negative 4 of f of x. And we just already found that f of negative 4 is negative 6. -6 does not equal -3, so it's condition 3 that is not met in this case. That's why our function is not continuous. So we have a discontinuity at x equals -4. Again, just like the last example, this is a removable discontinuity, because again, it's just that single point, not a jump. And then finally, on what intervals is this function continuous? So again, it's continuous before we get to x equals -4. And it's a continuous again after x equals -4. So those would be the intervals where our function is continuous. And here's one more example for us to answer those same questions. So is it continuous, yes or no? Well, no, it's not continuous. It's got a big old jump there in the middle, and that jump happens at x equals -1, so it's not continuous at x equals -1, or you could say we have a discontinuity at x equals -1. So why is it not continuous? We take a look at our three conditions. First of all, we take -1 and plug it into our function. Does that value exist? Well, f of -1 happens right here where that solid circle is, and it's equal to y equals 0 at that point. So yes, it does exist. Condition 1 is met. So that means we need to look at condition 2, and that's the limit as x approaches -1 of f of x. So here, we have to look at, so x equals -1 is right here. Let me put this in red, right here. There's x equals -1. And you can see if we come in from the left, that means we'd be following here and get closer and closer to x equals -1. We zero in on this point right here, which has a y value of 2. So that would be the limit as x approaches -1 from the right of f of x is equal to -2. Sorry, positive 2. But if we come in from the left instead, if we look at this limit, come in from the positive side. Oh, I switched those. I got those backwards. This one was plus. We were coming in from the right. This one is minus. We're coming in from the left. Sorry about that. Okay, so if we come in from this direction, we follow our graph in. As we get closer and closer to x equals -1, we get closer and closer to y equals 0. If the limit from the right and the limit from the left do not equal each other, that means the overall limit does not exist. So here, condition 2 fails. That's why it's not continuous. Okay, this discontinuity at x equals -1, this one is a non-removable discontinuity. Okay, again, because it's not just a single hole, it's an entire jump. Okay, the whole function just moves up and jumps 2 spaces up, so that's a non-removable discontinuity. And the intervals where this function is continuous, well, it's continuous from -∞ to -1, and also from 1 to infinity, just not, sorry, -1 to infinity, just not continuous at that point, x equals -1. Okay, so in those three graphs, we were looking at continuity and discussing continuity by looking at a graph, at a picture. So now we're going to discuss continuity by looking at an equation, okay? You could take the time to graph it, but we want to be able to just look at the equation and discuss the continuity there. So here, the directions say, for the following functions, identify the intervals over which the function is continuous. So they are asking, where are these functions continuous? And this first one should only take you about 2 seconds. Okay, we had that little fun fact back there with our definition that said polynomial functions are continuous over all real numbers. This is a polynomial function. It happens to be a quadratic function. So this one is continuous from -∞ to infinity. We don't even need to give it too much thought. Okay, this next one, part B, this is a rational function, okay? And our little fun fact about rational functions was that they are continuous over every number in the domain. So before we can answer where's this thing continuous, we need to figure out its domain. And remember that rational functions are undefined anytime we have a 0 in the denominator, because we can't divide by 0, right? 1 divided by 0 on your calculator, it would give you a big fat error. So we have to figure out where is the denominator of this function equal to 0. If I add 16 to both sides and then take the square root, don't forget when we do square root, we always throw in the plus or minus. So this function has a domain of all real numbers except positive 4 and negative 4. And that means that this function is continuous over all real numbers except positive 4 and negative 4. So this function is continuous from negative infinity to negative 4. It's continuous from negative 4 to 4, and it is again continuous from 4 to infinity. So it turns out the intervals over which it's continuous are really the same as the intervals of its domain. Okay, next one, also a rational function. So let's take a look here. Again, we need to consider its domain. So this time the denominator is x squared plus 16. Can that ever be equal to 0? I subtract 16 from both sides. X squared equals negative 16. That's immediately a red flag, because when we try to take the square root of both sides, we would get an imaginary number. So there is no solution here. So that means there are no numbers that we need to worry about excluding from the domain. So this function is also continuous over all real numbers. And our final one here, this one is a piecewise function. You've probably seen piecewise functions in your college algebra class. So basically this function has two definitions. It's either going to be x plus 2 or 14 minus x squared, depending on which x value you have. Okay, so our function definition depends on our x values. So the first part of this function, x plus 2. Well, think about what does x plus 2 look like? What's that graph? It is just a linear function. It's just going to be a straight line. So that function by itself would be continuous. It's continuous from negative 1 to 3, or it's even continuous on all real numbers. So that function we know is continuous. Our other definition we have, 14 minus x squared, that's a polynomial. Specifically, it's a quadratic, but we already talked about, one of our fun facts was that polynomials are continuous. So we know that this function is going to be continuous on its interval. But the key here, the trick is going to be what happens at the point right here, x equals 3, okay? Because we're going to use this function, x plus 2, that is going to happen for x values that are between negative 1 and 3. Okay, that's what that notation means up there. And we're going to use the second definition, the 14 minus x squared, for x values that are between 3 and 5. Okay, but what happens right there where they meet? What happens at x equals 3? So basically what we need to do is we need to look at the limit of f of x as x approaches 3. And in this case, that means we need to look from each side. We need to look to the limit f of x as x approaches 3 from the right. Try not to mix that up again. And we also need to look at the limit as x approaches 3. I did mix it up again. That's what you get, right? Okay, we need to look at it coming in from the right and coming in from the left. If those two values are equal, then we know we're continuous at 3. If those two values are not equal, then we're not continuous at x equals 3. Okay, so let's see. If we're coming in from the positive side, from the right, that means we need to use this definition, because that means we'd be coming in numbers that are slightly bigger than 3. Okay, so we'd be coming in from this side. So that means we would want to use this function definition. Okay, once we have figured out which function definition to use, this is just a straight up substitution. It would be 14 minus 3 squared, which is 14 minus 9, which is 5. For this limit coming in from the left, that means, let me switch colors here, it's getting kind of messy, let's do green. So if we're coming in from the left, that means we would need numbers smaller than 3, getting closer and closer to 3, but they would be smaller than 3, so we would use this function definition. So this would really be the limit as x approaches 3 from the left of x plus 2. Again, a nice easy limit. All we need to do is solve that by substitution. So we also get 5 for that answer. So that means, back to our question, where is this function continuous? It is continuous from -1 to +5. Now the question might be, why is it not continuous from -infinity to +infinity? Well, this function is only defined on a limited domain up here by this notation with your piecewise function. It starts at -1 and ends at 5. Okay? If we would have gotten 2 different answers right here, it would have been continuous from -1 to 3, and again from 3 to 5, okay? But since our answers matched, we don't stop and kick out 3. It's continuous on that whole closed interval. And that's it for our discussion on continuity.